All right, guys, let's take a look at exponential relationships. So you guys have done linear relationships, you've done quadratic relationships, and now we're on to our third type, which is exponential. So what you want to look at here is what happens not to the first difference, well, kind of to the first difference, but if you notice here, when you have this sort of thing, 2, 6, 18, 54, all that stuff here, you notice the first differences are not the same. So when you subtract 6 from 2, or 2 from 6, sorry, and you went up 4, then you went up 12, and you went up 36, and you said, wow, well, that's not, first differences are the same. So usually what we would do is go to second differences, and we would find that they're the same, and then you would say it's a quadratic. So first differences were the same, it's a line. If second differences are the same, it's quadratic. But in this case, they're not the same, neither first nor second. So you do notice one thing though, or you might not notice it. Honestly, you probably wouldn't notice it. But what you can do is you can go, and if you look here at this term to this term, what you've noticed is that 2 times 3 is 6, and 6 times 3 is 18, and 18 times 54, no, 18 times 3 is 54. Or 6 divided by 2 is 3. So if you go this divided by that, you get 3. This divided by that, you get 3. This divided by that, you get 3, etc., etc., etc. And they have what we call a common ratio. And if that's the case, you have an exponential relationship. Okay, so first difference is linear. Second difference is quadratic. Ratio, exponential. L, Q, and E. Okay, so if the ratio is the same, you have exponential. And that is just a little blurb on that. Okay, the graph increases. So when you look at the graph, what you notice is the graph goes up like this. It kind of looks like half a parabola, but it's not. Okay, and we'll get into that a little bit more. Oh, what's going on? We'll get into that a lot more actually as we move through this unit. But you'll notice it's flat here. It doesn't go underneath this axis. It gets close to it and it flattens out if you're moving to the left. But as you move to the right, it goes up and it gets up. And it grows faster and faster and faster, and that's exponential. Okay, it's nonlinear, which means it's not a line, and it is increasing and moves upwards, and that is exponential growth. Okay, so increasing, remember we read it this way, like we read English, we read left to right. So a line or relationship is increasing if it's going up. Now, remember, I'm calling this a line. Linear is straight line. Okay, so you have a straight line, pretend that's straight, or like that, or whatever, but that's linear. Okay, so a connected bunch of points to make a line is not necessarily linear. Exponential decay is the opposite of exponential growth. I don't know if it's the opposite, but decay goes down. So you have exponential relationships that are growing or decaying, and we'll get into that a lot more as we move forward. The way you know a relationship is exponential is by its shape and by the ratio being the same. But the way you know it's exponential in an equation is you look to see that sort of setup, y equals a to the x. And the key is this. The x, or the variable, is in the exponent. So instead of having x squared, where you have a quadratic, okay, you would have something like 2 to the x, where it's the x, they've swapped out with the constant, and the variable is up here. And if you have anything, 2 to the x, 10 to the x, 2/3 to the x, even if you have something like this, 6.7 times 1.3x plus 1, it wouldn't matter what it is. If you have an x, the variable, if it's up top, if it's an exponent, then you're going to have some sort of exponential relationship. When you look at these two here, you have 2 to the x and 3 to the x. What we're going to look at now is what happens to the graph shape if you have a bigger number compared to a smaller number. And what happens is, I'll do this guy in purple, okay? So I'm going to start over here. So 2 to the x, you go 2 to the power of 3, which is 8. So that's 8. So over 2 up 8, which is right here. Then 2 to the power of 2 is 4, which is, oh, that was, I'm sorry, that was 3. 3, 8. 2, 4. 1, 2, 3, 4. 2 to the power of 1 is 2. 2. A lot of mistakes today. And then here. and then you get a half, a quarter, and an eighth. Now, how you get that is that's 2 to the negative 1. Now, you can just throw that in your calculator, or you can remember from what we were looking at previously is that 2 to the negative 1 is the same as 1 over 2 to the 1, okay? And 2 to the negative 2 is the same as 1 over 2 to the 2. But if you put in a calculator, that's fine, okay? Just get a decimal, okay? 0.5, 0.25, and 0.125. It really doesn't matter all that much because what you're going to notice is when you go to plot these, it's going to flatten out. These numbers are getting smaller. As the x gets bigger, the y value is getting smaller and smaller and smaller. So if you threw this in the calculator, you'd see that. But the key is when you plot these, okay, and all I'm going to ask you to do when you plot these is get closer and closer to the 0 line, but don't cross it. Okay, don't cross that axis, just leave it like that. So the left side of the graph is not as important as the right side of the graph. The right side you want you want to take a little more care with when you compare, because you're going to notice here there's going to be a difference between 3 to the x and 2 to the x. So if I go 3 to the x, I'm going to start at the bottom here. That's 3 cubed, which is 27. So 3 and 27 doesn't even fit on the graph. Okay, we'll leave that for a second. Then if I go 3 squared, I get 9. So 3 squared is 9. So I plot the point 1, 2, 3, 2, or 2 and 9. So it's right here. 3 to the power of 1 is just 3. Okay, and again, if you get confused with this stuff, just throw in your calculator. 3 to the 0, anything to 0 is 1. So that goes there. And then after that, don't worry about the left side. Okay, again, it flattens out. But the key is that 3 to the x grows faster than 2 to the x. Okay, the orange line is steeper than the purple line. And if we had 5 to the x, it would be like this. And if I had 1.5 to the x, it would be like this. Okay, the bigger the number, the steeper the line. Okay, and the left side, don't worry too much about. Okay, except they all cross at 1 and they all flatten out. Okay, they will crisscross, but honestly, look at this mess, right? It's hard to graph, and the important thing is not, because in reality, when we're looking at things in reality, in the real life questions and in real life, this is what we're looking at. We're always looking at usually we're looking at the positive numbers, not the negative, because they don't really happen in real life, right? If we're talking about how many years, what's the population of fish in a pond or something like that over a certain amount of years, or how many cells are there in your body in a certain period of time, or whatever it is, right? When you plug in a value for the time, it's not going to be negative. You don't have a negative time value, right? It's going to be 2 days, 15 seconds, whatever, 12 years, but it's always going to be positive. So we're more concerned with these numbers over here than we are with the other ones. Okay, so the bigger the number, the steeper it is, and you're not going to like this. But what happens here is if you have fractions, okay, fractions are going to be the opposite of what you saw above. So 1/2 is going to be the opposite of 2 to the x. So people don't like this much, but if you put 1/2, and you know what, just use your calculator, I guess. Easiest way to do it, put 1/2 into 1/2 to the power of something into your calculator. So if I go 0.5 cubed, you're going to get 0.125. If you put 0.5, which is 1/2, squared, you're going to get 0.25. 0.5 to the 1, 0.5. This is going to be 1. And then when you get these numbers here, 0.5 to the negative 2, for example, you're going to get 4. And when you graph these, you're going to know that once you graph it, you're going to take a little more care than me. It's going to be, if you compare 1/2 to 2, the numbers are kind of the opposite. Negative 3 turns into 3. 2 turns into negative 2, vice versa. Okay? And you get that graph that look like that. 1/3, you can do the same thing. You can go ahead and say 1/3 to the 3 is 1 over 27, or throw it in a calculator. And what you'll find is these numbers here are the opposite of the numbers that you see for 3. Okay, 3 is your base. Okay, so not as important as this. Okay, so really what I want you to do is know that the bigger the number, the steeper it is. And if these numbers are fractions, though, they are decreasing. Okay, and this is called exponential k. Okay, the other ones were called exponential growth because they're increasing. These guys coming down are decreasing, so they're decay. So let's go over what we're taking from this one more. 1, ratios. Okay, are the ratios consistent? Not first differences, not second differences, but are these numbers here growing by the same ratio? 6 divided by 2, 18 divided by 6, 54 divided by 18, 3, 3, 3, 3, 3, exponential. Is the shape kind of like this? If it is, exponential, okay? Do we have an x in the exponent? Yep, exponential, okay? Which guy is steeper, 2 to the x or 3 to the x? Well, 2 to the x is not as steep as 3 to the x. This is a bigger number, so this guy here, the orange guy, is going to be steeper. Okay, these are exponential growth because they're growing, they're getting bigger. These ones here are decay because this number is less than 1. Okay, and that's all we're going to take from this really is decay numbers have bases that are less than 1. Growth have bases that are bigger than 1. The bigger the base, the steeper the curve. Done. That's the takeaway from today. If you get that, you're in great